Right, so in this video here we're going to have a look at the tangent function. So right back at the beginning of the topic we introduced how tan is defined in the unit circle. I looked at the basic graph of tan x back in one of those earlier videos, and then since then we've really just been focusing on graphs of sine and cos, equations involving sine and cos, and now we're going to go back and think about equations and graphs involving tan. The reason we separate tan is because actually, particularly the graph is very different, and so you know, the logic is a bit separate to what it is for sine and cos. So we get all those things right for sine and cos, and then we can add on the tan graph at the end. In terms of the equation solving, that's exactly the same as what it is for sine and cos functions, just obviously thinking about solutions in different quadrants, but other than that the process is the same there. But let's just work our way through some examples involving tan. Okay, one thing that's really important involving tan is that there's this connection between sine and cos and tan, okay, in that sine theta over cos theta is actually equal to tan theta. And that's because if we go back to these definitions of the fact that this y value here is tan, so this is tan of x, or tan of theta, I'll say, sorry, let's make that theta. The x-coordinate of the point P is cos, so this distance here is cos theta, okay, along the bottom of this blue triangle, and this vertical distance in the blue triangle is sine of theta. If we draw out those two triangles separately, so if I look at the blue triangle that's already drawn in there, in the unit circle, okay, that's a triangle where if that angle's theta, this length is 1, it's a unit circle. That's sine of theta, and that is cos of theta. If we then look at the bigger triangle out to the tangent, okay, this is theta, this is 1, again, unit circle, and this is tan of theta. When we do that, we can see that A, they're similar triangles because they've got the same angle, and they're both right angle triangles, they have the same angles, and so therefore we can use the similarity ratios in that sine divided by cos is equal to tan divided by 1. So we get this idea that sine of theta divided by cos of theta is equal to tan of theta divided by 1. And so we get this connection that tan theta is equal to sine theta over cos theta. And that's important in a number of different equations and algebraic manipulations, and it's important to bear in mind when dealing with tan. We also note from our definition of tan in the unit circle that tan is undefined when the angle produces a line that is parallel to the tangent. So that is at the odd multiples of pi on 2. 1 pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, etc. So we can express odd numbers as 2k plus 1, where k is an integer. Take any integer, double it and add 1 to it, you'll have an odd number. And if you multiply that by pi on 2, you've got all of the points where tan is undefined, and so on the graph that's going to be the asymptotes. Okay, let's solve an equation and then let's have a look at the graph. So its process is still the same. Get the tan on its own, identify your exact value, identify which quadrants your solutions are in, and use your domain. Now, we haven't been given a domain here, sorry, that's an error. Let's make the domain, let's just go 0 to 2 pi. Okay, so tan of, actually I might just make it, no, that's okay, 0 to 2 pi I think. So tan of 2x minus pi on 3 is going to be equal to 1 on root 3. Okay, so we've got the tan on its own. We need to think about our exact values. Half the equilateral triangle, 1 on root 3, we need 1 to be the opposite, root 3 to be the adjacent, and so we're looking at pi on 6. Tan is equal to something positive. So again, thinking about the definition of tan as being that y-coordinate on the tangent, that happens in the first and third quadrants. Okay, so pi on 6 up from there and pi on 6 down from there. Okay, solutions out of the unit circle are going to be equal to 2x minus pi on 3. Then we will add pi on 3 and they'll be equal to 2x, and then we'll be dividing by 2 and they'll be equal to x. Okay, so that is going to be, we want x to be between 0 and 2 pi, which means we want 2x to be between 0 and 4 pi, which means we want 2x minus pi on 3 to be between 0 minus pi on 3, which is negative pi on 3, and 4 pi minus pi on 3, which is 4 pi is 12 pi on 3, so that's 11 pi on 3. It's still 2 laps of the circle, it's just starting at negative pi on 3. Now in this particular instance, that's actually not going to make a difference, as if we had just done 2 laps from 0 around to 4 pi, and that's because there is no solution in this little range here to capture, and so it actually isn't going to make a difference. So if that's negative pi on 3, that makes that 0. We're coming around here, that will be pi. We're coming around again, this will be 2 pi. I'm coming around again, this will be 3 pi. And finally around to finish here at what would be 11 pi on 3. Okay, so 4 solutions: pi on 6, pi plus pi on 6, which is 7 pi on 6, 2 pi plus pi on 6, which is 13 pi on 6, 3 pi plus pi on 6, which is 19 pi on 6. Okay, what did we say there? 1 pi on 6, 7 pi on 6, 2 pi plus pi on 6 is, nope, sorry, 13 pi on 6, and 19 pi on 6. Now the difference with tan is that all of the solutions are the same distance apart. Every one of the solutions that came out of the unit circle is pi apart. So actually, once you get your first solution, you can then just keep adding on pi until you get to the end. Okay. So we've got our 4 solutions out of the unit circle. We now want to add pi on 3. Pi on 3 is the same as 2 pi on 6. So we're going to do that. We're going to get 3 pi on 6, 9 pi on 6, 15 pi on 6, and 21 pi on 6. All of those will simplify. I think I'll just leave my simplifying to the end. I'm going to divide everything by 2, which will make my denominators 12. So 3 pi on 12, 9 pi on 12, 15 pi on 12, and 21 pi on 12. Okay, we've got the common factor of 3 in all of these. So that is pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4 are our solutions to that equation. Okay, the graph. So if you go back to an earlier video when we introduced these graph shapes out of the unit circle, you can have a look at where this comes from. So we recall that the y equals tan of x produces this graph. Now remember, the difference with tan is we only need to actually look from 0 to pi to see one complete repetition. Okay, if you just look at that shape there, so this bit here with an asymptote in the middle, that is one complete period. And then all we're doing is repeating that again and again and again. So get, again, like any other graph, get that first period right, and then you're good to go. A couple of things I want you to note about the graph of tan. Okay, the points of inflection are not stationary points of inflection. Okay, these are not like cubic graphs where we go stationary and then again. Okay, you're just going to have a light bend there at the point 2x. Remember, we've talked about earlier that actually the definition of a point of inflection is where the tangent actually cuts through the graph. So when I draw a tangent down here, the tangent sits, completely above the graph. When I draw a tangent up here, the tangent sits completely below the graph. If I draw the tangent here, it's still below the graph. It'll cut through it down there somewhere, but at the point where it touches, it stays below the graph. Okay. The definition of the point of inflection is the point where that tangent will actually cut through the graph. So at this point, the tangent's going to go under the graph there and over the graph here. Okay, sorry, it's not the best tangent that I've drawn there. But essentially it's going to do that. And that, therefore, is the point of inflection. After that point, that tangent will stay under the graph. Before that point, that tangent will stay above the graph. Okay, so they're not stationary points of inflection, but they are points of inflection. We also want to note that the period of the tan graph is pi, not 2 pi. And the tan graph doesn't have amplitude. So we can't talk about the amplitude of a tan graph. But doesn't mean you can't still dilate the tan graph. And this is something that's really important, okay? If I ask you, let's go back to something really simple. If I ask you to draw me the graph of y equals x squared, we know it's a parabola with its turning point at the origin. If you just draw that for me, that's not sufficient. Okay, and that's because I can't tell whether this is y equals x squared, y equals 2x squared, y equals 70x squared, y equals 7.6x squared. Okay, so you would need to give me at least one point on this graph that gives me a sense of the dilation of this particular parabola. The same is true of the tan graph. If you just draw this tan graph with no other scale, how do I know that this isn't 2 times tan x, or 10 times tan of x, or half times tan of x? Okay, how do I know what the dilation is? And that's where a key point is going to be helpful here. There's a really obvious key point, because if we think about our exact values, we all know what tan of pi on 4 is. Remembering that pi on 4 comes from this special triangle here, the isosceles right-angled triangle, and so when you work out, sorry, that's not root 3, that's root 2. When you work out what tan of pi on 4 is, tan of pi on 4 is opposite over adjacent, it's 1 over 1, it's 1. And so therefore, the most obvious point we could put on the graph is when x equals pi on 4, y equals 1. So it goes through the point pi on 4, 1. So that point there, which means if we all of a sudden made this graph 2 times tan of x, this point would become pi on 4, 2, okay? Because we would have stretched the graph by a factor of 2 from the x-axis. And so it just gives us a reference point for, a point on the graph that we can transform so that we can also reflect the dilation in our sketching of our graph. Otherwise, the transformations are the same. We don't call it amplitude. We can still, doesn't mean we can't dilate the graph. So A will dilate the graph by a factor of A from the x-axis, modulus of A, so you can't have a negative dilation factor. The negative is about reflecting the graph in the x-axis. N will dilate the graph by 1 over n from the y-axis, which will mean the period that was pi becomes pi divided by n, not 2 pi divided by n. Okay. If n is negative, then we'll reflect this graph in the y-axis. B is about horizontal translation, and C is about vertical translation. Okay, so let's sketch some graphs. Okay, so in this example, we're looking at sketching the graph of y equals tan of 2x minus pi on 2. Okay, so the first thing we need to be careful about here is that the period change is interfering with the horizontal translation in the current format. In the current format of the equation, we would actually need to do the horizontal translation before we do the period change, and that's complicated when you're trying to sketch a graph. So you want to try and have the same routine. So if we take a moment to write the equation in the standard format, then that will help us. So this is y equals tan of, if we're factoring the 2 out in the bracket, we get x minus pi on 4. Okay, so the 2 here is a dilation by a factor of 1/2 from the y-axis. So all the x values are being halved, so that means the period's going to change. So the period of a regular tan graph is pi, and so the period of this tan graph will be half of pi. Then we've got this minus pi on 4, and so that is a translation to the right by pi on 4. Okay, let's focus on getting the graph right, forgetting about the translation for a minute. I want to just quickly have a look at what one basic tan graph looks like, not forgetting this particular function for a minute. So, sorry, I mean one period of a tan graph. So, if you haven't got any translation, your tan graph is going to start at the origin, and then at the whatever the period is, you'll have another x-intercept. Halfway along that period, you'll have an asymptote. Didn't really draw that very well halfway. Let's try that again. Okay, so halfway along that period you'll have an asymptote, and a quarter of way along that period you'll have that key point. Okay, so this point, that's going to give you that sense of dilation. So let's just think really generally. So this point here, this x value here, is equal to whatever your period is. Then if you translate it, you can work it out from there. Your asymptote is x equals half of your period. Okay, and your key point is going to be at 1/4 of your period, and then whatever the a value in the function is, which in this case is 1. So for this function, our period is pi on 2, so that will be pi on 2. Our asymptote therefore is going to be half of pi on 2, which is pi on 4, and our key point would be a quarter of pi on 2, which is pi on 8, and the a value in this case is 1. Okay, so there's one period, and then we're going to need to focus on moving all of that to the right by pi on 4. Okay, so let's get that sort of mapped out. Oops, sorry. Okay, so 2 pi, halfway along there, somewhere about here, is pi. Half of that is pi on 2. Half of that is 3 pi on 2. And then halving again for units of pi on 4, which is going to help us with the translation and also the period of pi. So in terms of with sine and cos graphs, we talked about the need to sort of divide your period into 4 to be able to get the graph shape right. In this case, you really only need to divide the graph in half to get your asymptote happening halfway along. Yes, your key point will happen a quarter of the way along, but you only need to mark that in one period, so I wouldn't probably scale your axis according to that. Okay, so again, let's think about what this graph looks like without the translation. So I'm going to just use my pencil, well, my electronic pencil, i.e. a grey pen. Okay, so starting at the origin, finishing at the end of the period, asymptote halfway along the period at x equals pi on 4, and then, try that again, let's have key point at pi on 8, 1. Okay, so that's our graph without translation. Maybe sort of get some symmetry about that point. Okay, so now we want to move the graph to the right by pi on 4, which means my first x-intercept is going to happen here at pi on 4. My next intercept happens at pi on 2 plus pi on 4, which is 3 pi on 4. The asymptote also moves across to the right by pi on 4, so it's now at x equals pi on 2. Okay, and then this point is also going to move to the right by pi on 4. So I'm only going to mark the point once, I'm just going to do that. So pi on 8 plus pi on 4, so that's pi on 8 plus 2 pi on 8, so it's going to be at 3 pi on 8. Okay. Alright, so 3 pi on 8, 1. Okay, so there's one complete period. And then we just need to be able to replicate that. So what we notice is that our x-intercepts are always a whole period apart, which is pi on 2 apart, okay? Which is 2 markers on my x-axis apart, because each marker is at pi on 4, is pi on 4 apart, sorry. So my next x-intercept will be here, my next x-intercept will be here, and my final x-intercept, that's my final x-intercept. My asymptotes are always also a whole period apart, okay? So it should be a period between the asymptotes, so pi on 2 between the asymptotes. So my next asymptote is going to be here at pi. The one after that is going to be here at 3 pi on 2. And the one after that will be at 2 pi. Okay? And then I really should have enough, and so that means the y-intercept is also an asymptote. So I now should really have enough information to be able to draw in my tan graph. Try and get some symmetry about the various branches. Remembering that the point of inflection in the tan graph isn't a stationary point of inflection. Okay. Right, marking key points. You've just got your 1, 3 pi and 8, 1 marked. You don't need to mark that repeatedly on each branch. Asymptotes, x equals pi on 2, x equals pi, x equals 3 pi on 2, and x equals 2 pi. Okay, so they must be marked with equations. The points there aren't enough. And then intercepts, so this is pi on 4, 0. This is then 3 pi on 4, 0. You can just count 1, 2, 3 pi on 4, 4, 5 pi on 4 is the next one. 6, 7 pi on 4 is the next one. And that's the final one. So the purple graph, I'll just erase some of the grey graph so that it's sort of adding a bit of confusion there. The purple graph is our graph of y equals tan of 2x minus pi on 2, which is the same as tan of 2 times x minus pi on 4. Alright, let's think about some other equations. So again, we're coming back to this idea that we've got this tan theta equals sine theta over cos theta, which I talked about earlier, and that can be a really helpful process in solving equations of a certain form. So if you've got sine of nx equals k times cos of nx, or that k could be on the other side as well, but if you've essentially got sine and cos, both with the same thing in the sine and cos, you should be able to change it to a tan function and solve that equation. So for example here we have sine of 2x equals cos of 2x. If we divide both sides of this equation by cos of 2x, we get tan of 2x on the left hand side equal to 1 on the right hand side. And then it's about solving an equation. Tan equals 1. What's the exact value for that? Pi on 4. Okay. Tan is equal to positive 1. So our solutions are in the first and third quadrants, pi on 4 and pi on 4. And we are finding solutions where x is between 0 and 2 pi, which means that 2x will need to be between 0 and 4 pi. So we get 1, 2, 3, 4 solutions as we move around the circle. Okay. So I just did the fact that x has to be between 0 and 2 pi, which means at my previous line of calculation, 2x will need to be between 0 and 4 pi. Okay, so we get 0 plus pi on 4, which is pi on 4. We get pi plus pi on 4, which is 5 pi on 4. We get 2 pi plus pi on 4, which is 9 pi on 4. And we get 3 pi plus pi on 4. 3 pi is 12 pi on 4, plus pi on 4 will be 13 pi on 4. Again, you should be able to think about these are all just add pi, add pi, add pi. Dividing them all by 2, they're going to be over 8. So pi on 8, 5 pi on 8, 9 pi on 8, and, rewrite that, 13 pi on 8. 4 solutions to that equation. Alright, just one more equation, I think. Yep. So again, thinking about using the fact that sine divided by cos is tan. So again, if we divide both sides here by cos of 3x, dividing by cos of 3x, we're going to get left with tan of 3x on the left-hand side, and we're going to get 1 on root 3 times 1, so just 1 on root 3 on the right-hand side. Okay, so exact values, half the equilateral triangle, 1 on root 3, which means we must be talking about pi on 6. We're looking at tan being equal to a positive value, so again, our solutions are in first and third quadrants. Should have made one of the equations in this section negative, shouldn't I? Pi on 6 and pi on 6. We're going to get solutions. I'm just going to move this over so that we've got room for our solutions. We're going to find solutions for 3x, and then we're going to divide them all by 3 to get our solutions for x. Now we want x to be between negative pi and pi, which means we want 3x to be between negative 3 pi and 3 pi. Again, I find it easier to do the positives and negatives separately, personally. So let's start at 0, let's go around to pi, let's go around to 2 pi, and again around to 3 pi to get our 3 positive solutions, 1, 2, and 3. So I'll leave room for my negative one. So my positive solutions are going to be pi on 6, pi plus pi on 6, which is 7 pi on 6, and 2 pi plus pi on 6, which is 13 pi on 6. My negative solutions, if we go back the other way, again, so let's start, oh sorry, I lost my unit circle in all that. Okay, so let's start at 0, we'll use a different colour. So start at 0, we'll go back the other way to negative pi, back around to negative 2 pi, and around to negative 3 pi. So we get 1, 2, 3 solutions. Okay, so the most negative one is negative 3 pi plus pi on 6, so that's negative 17 pi on 6. The next one is negative 2 pi plus pi on 6, which is negative 11 pi on 6. And then the least negative one is negative pi plus pi on 6, that's negative 5 pi on 6. Again, you can just add or subtract pi between each answer. We want to divide them all by 3, so our denominators are going to become 18. So we're going to have negative 17 pi on 18, negative 11 pi on 18, negative 5 pi on 18, pi on 18, 7 pi on 18, and 13 pi on 18. And so there's the solutions to the equation. So processes for solving equations the same, potentially just the extra added use of this connection here between sine, cos and tan to create a tan equation that perhaps didn't initially seem like a tan equation. Taking some care with sketching your graphs, making sure to label an additional point to be clear about any dilation from the x-axis. Asymptotes all labelled with equations, making sure your asymptotes are spaced 1 period apart, as are your x-intercepts 1 period apart. Thinking about this sort of general sense of what one tan period looks like, start of the graph, end of the period, asymptote halfway along the period, key point quarter of the way along the period. Okay, and then equation solving otherwise is the same as it was for sine and cosine graphs.